Hi, this is Jim Kim, and our team, Min, Joseph, and I are going to talk about the project on Amazon's locker system. I will start with the problem description. Joseph will going to talk about mathematical model and MIT model. Min is going to talk about MATLAB model, and I will wrap up with comparison of two models and conclusion. So the goal of this project is to build a model using different softwares to come up with the optimal number of lockers to be assigned. We have 30 possible lockers in Max to locate, and we want to optimize the number of lockers to be assigned to minimize the cost while covering all 300 customers within 30 kilometers. It costs $50,000 for each locker and $100 for every kilometer traveled by customers. Here we have a graphical representation of all the customer location in blue and possible locker locations in red. Assuming the yellow circle has a radius of 30 kilometers, we want all the blue points to be covering when the center of yellow circle is located to each red point. Here what we want our model to do is to eliminate or reduce overlapping areas of yellow circle. What the MIP model is going to do is to get the very optimal solution by going through every location and get the minimal cost. However, what our MATLAB model using simulated annealing is going to do is randomly select a locker location and calculate the traveling cost for all the location that is within 30 kilometers and give penalties that are more than 30 kilometers. And because the model is randomly selecting a locker's location, the result will be different or less efficient than the model result.
Hello, this is Joseph Gualiardi, and I will be talking about our mathematical notation and our MIP model. As you can see, we have two decision variables, XLC and YL. XLC is which locker to which goes to which customer, and YL is which locker we are choosing from 1 to 30. L is locker, C is customer. If you come down to the minimize equation, we have $50,000 as a cost per locker chosen, plus the cost, basically the distance cost. So there's $100 per kilometer, which is our distance equation, times which lockers go to which customers. We have a few constraints as well, two binary constraints. Both our variables are binary. Our first constraint, besides that, is all lockers purchased must be less than or equal to 30. We can only purchase up to 30 lockers. The second constraint is that every single customer must be covered by a locker, so it equals 1. And the last constraint is the distance from any locker to a customer must be less than or equal to 30. And finally, we have our linking constraint, which links our XLC to our YL. As you can see from this equation, XLC can never be 1 when YL isn't, but YL can be 1 when XLC isn't. But this would never happen because this is a minimize equation, a minimize function. Here's our MIP model, and as you can see, we have our lockers 1 through 30, customers 1 to 300. We have the cost of purchasing a locker and the cost per kilometer traveled. And then here's our giant distance equation matrix. Then we have our dot mod model. And so once again, we've defined all of our variables up here. We have our minimize equation, which we talked about in the mathematical notation. And also we have our constraints that we laid out down here. And as you can see, we arrived at the correct solution based on this. $816,400 is our cost. This amazing software with IBM Cplex even shows you which lockers were chosen from our equation. So that's what YL shows. And if I brought up XLC, it would give you a giant matrix of which lockers went to which customers. Thanks for listening, and now we will have Min discuss our heuristic.
So today I'm going to talk about our heuristic to the Amazon problem. So there are three parts of it. So the first one would be the data import, and the neighbor creation. So here I import the matrix data, and the data matrix is the distance between each locker to each customer, and this and the matrix is just the distance, the distance from customer to its nearest locker, and I put it to 31. It's 100 by it's 300 by 1, and the distance matrix is 300 by 30. So, and the way that I create the neighbor is by basically using the swap method from a generic algorithm, and also I will randomly add 1 or 0 at any position, at random position. And also the pick matrix is 30 by 1, which is which will show which locker we're gonna choose. So as you can see, at the beginning I assign randomly 8 locker into the first 8 positions, and the loop will run through it again. And here is our first loop. So basically I'm just gonna run and let's try to run the 10,000 integrations. Alright, so the second part is assigning locker to customer and calculate the cost function. So first of all, I will predetermine the total all will be a very big number so that I can change it later. And for this is the first loop to identify which locker that we are using. As you can see, from 1 to 30, if it's equal to 0, that means we choose that locker at that positions. And then after that, I will go through everything to assign the smallest, the nearest distance to the C matrix. And after that, I will this is the penalty. So if in the C matrix, if anything is bigger than 30, because our constant is that the farthest that the customer can go is only 30 kilometers. So we're gonna give them a fine if they do that, and that will count into the total. And then the total is gonna be the sum of the C, which is the total distance from each customer to their nearest locker, time 100. And the sum P is the number of locker that we choose, times 50,000 plus the fine. But our purpose to get the fine to be equal to 0. Alright, and then this is the last part, the stimulated annealing method. So as you can see, right here is the T we set equal to 0, and every time it go through an iterations, it's gonna we gonna time it by 0.999, and by calculating that, if the total number is less than the total all, then we definitely gonna choose that, and the M matrix will be represent as the P will be equal to P, and the CC will be to C. F is the fine, and same here for this one. If a random number from 0 to 1 is bigger than or equal to P, then we're gonna take that as a our result. And here is our number versus the optimal result that we have based on the OPL, IBM OPL, and our result indicate that we should have 14 lockers with a total price of about $1,088,300, and the fine is 0, which means that every customer is like 30 kilometer or less from this place to the locker. And so I'm gonna run a simulation. So this is the algorithm in MATLAB. As I explained in the PowerPoint, here I'm going to run a demonstration of that. Also through our experience, I know that if we put the integration into 10,000, it will not give us the optimal result. And now let's try 10 millions result integration. All right. Just take some time for it to run. It's pretty long. Alright, and here is the optimal result, but it's not the same as what we had before, but it still gave us a result right here. I know it's gonna differ for time to time, so because this is a random generator. Alright, thank you.
Through our experiment on IBM OPL and MATLAB, we got 8 lockers as our optimal number of lockers and $816,400 as the minimal cost. The MATLAB model gave us a result of 11 lockers and $1,190,500. To see the efficiency of the result of MATLAB model, we divided MIP model result by the MATLAB model result. And we got about 73% efficient when comparing the number of lockers and 69% when comparing the total cost of the locker system. And the runtime of our MATLAB model was 55.5 seconds. This project, even though its sample size is not that big, we got the experience to deal with a real-life problem. As a team, we analyzed what the goal of this project is. We built a mathematical model, and based on that, we constructed MIP model and MATLAB model. We compared two models to see how efficient the MATLAB model is, and we learned that because it is randomly selecting locker locations, every results are slightly different. But the overall efficiency of the MATLAB model is about 70% when compared to MIP model. Thank you for listening to our presentation.